Good morning, everyone. Hope you had a great weekend. Today, we are covering rational functions. Last class, we talked about polynomial functions and their graphs, and I gave you some homework problems to do. I told you don't do anything out of the packet. So let me take you to that. Here were the set of steps that I gave you to sketch a polynomial function. And then I gave you these problems to look at. I told you 31, 32, 33, 34, you should be able to do 35, 36, try them if you want. We can talk about them today. So first, any questions over 31, 32, 33, or 34?
I have a question.
Yes.
I was wondering, so on 31, was the GCF X? Because that's where I noticed where I was messing up is I figured I would get the degree and the LC, but then when it would come to the GCF, I noticed that's where I was messing up. And I didn't know if the GCF was just X on that one, because I mean, I could do X squared. Well, I mean, I didn't know if we could do X squared or X because the 4X is only one X. So I figured it was just X.
Yeah, just X. I can run through this real quick. Okay. The degree of this polynomial is 3, and the leading coefficient is -1, right?
Yes.
And so it should go up on the left and down on the right, according to this chart that we have here, right?
Mm-hmm.
And then when you go to set it equal to 0, okay, this would be the next step. We set it equal to 0. We can pull out a GCF of X, and that leaves us 4 minus X squared equals 0, right?
Yeah, that's what I got too.
Okay, so that's good. There's one more thing you have to do, though. It's a little tricky. You set this equal to 0, right? Mm-hmm. This actually factors. You can go and turn this into a difference of squares. So it should turn into 2 plus X, 2 minus X. Maybe I should do it this way. So that step right there is necessary because now when you set each of these equal to 0, you get 0 here. If you set this one, go ahead.
Negative, that would be the -2, isn't it?
-2.
Yeah,
and then this one gives you +2. Okay, good. Yeah. So we have 3 X-intercepts. And then you have to determine the multiplicity, which is whether or not you bounce or cross. And that's when you look at the powers on these factors. And all of them happen to have a power of 1. And for multiplicity, we're looking at the power and we're looking at whether or not it's even or odd. And in this case, all of them are odd, right?
Yes.
So that means we will cross at each of these. Cross.
Okay. So if it's a positive, it'll bounce then, correct?
No. If it's an even number, it'll bounce.
Oh, an even number. Okay.
Even number. So if any one of these was squared, we would bounce there. If it was cubed, we would cross. If it was to the 4th power, we would bounce. Does that make sense?
Yeah, that makes sense. Even, bounce, odd, cross.
Yep. And I think, I have it in the notes from last class somewhere. Here we go. Multiplicity. If the multiplicity is odd, we cross. If the multiplicity is even, we bounce. And the multiplicity is the number up here on the factor.
I see. Okay. Thank you.
Yeah, I'm just going to draw the graph because we're pretty much done. We just have to put the X-intercepts at 0, 2, -2. We know it goes up on the left and down on the right. And then we're just going to connect these all together. And when we get to the X-intercepts at all of them, we're crossing. And that just means go through the X-axis to the other side and come back up through the X-axis to the other side, through the X-axis to the other side, and just connect it.
Okay.
I was having questions with problem 32 because I got X plus 1 and turned that into X equals -1, but I wasn't sure how, because I looked on the chart online. It was like a website and it said it goes through X plus 1 as well. So I was kind of confused.
Okay, so are you okay with the idea that this goes up on the left, down on the right? Is that all right?
Yes.
Okay, so you set it equal to 0. And did you pull out a GCF?
Yes, I pulled out X.
Okay, and if you do that, you're left with 1 minus X squared, right?
Yes.
And then you have to do difference of squares on that also. So that turns into 1 plus X, 1 minus X. That might be the step that you had an issue.
Yes, I did.
Yeah. See, this gives you both answers.
Okay.
So did you just look at this and say, oh yeah, if I plug in 1, I get 0?
Yeah, because I got X plus 1 and X plus 1 side by side. That's what I did.
Okay, yeah. So just remember that the formula we're using is that if you ever have something squared minus something else squared, it'll be equal to the A plus B times the A minus B. So these are always going to have a plus here and a minus here, which is why I have a plus and a minus right there.
Okay.
A question on that, that formula.
Yes.
So you're saying, so A squared minus B squared, but like, let's say in the question, the X in front isn't squared.
The X, okay, well, we're not factoring that part. We're only looking at this part. Is that what you're saying?
So wouldn't the 1 also have to be squared?
Okay, good. I'm glad you asked. 1, okay, so you have to realize that 1 is actually 1 squared. Maybe that's the issue. See, do you agree that 1 squared is 1?
Oh, okay.
Right. So here, the A we have is 1. And then kind of the B in the formula is the X. So we have something squared minus something squared. It might be easier when you have like 4 minus X squared. It might be easier for you to see that that 4 is 2 squared.
Oh, okay.
Minus X squared. And that's why this becomes 2 plus X, 2 minus X. Does that make sense?
Yes.
Okay. When it's a 1 though, well, 1 is 1 squared. So you just use the 1. Okay, so this graph, I'm going to show you, it should look a lot like the last one. It should go like this. It should cross through. Oh, whoa. Oh, I missed it. Okay, you get the idea. Okay, any issues with 33 or 34? Those are okay. Why don't we look at 35? Okay, because we didn't do 35 last time, or we didn't do one like 35. So let's start today with that, and then we'll get on to rational functions in a moment. So we're trying to graph this polynomial function. So the first step for us would be to identify the degree. The degree of this is 4, and the leading coefficient is actually a 2. So the degree is even, and the leading coefficient is positive. And so if we go look at that little chart, if our degree is even, we're looking here, and our leading coefficient is positive, we're looking here. So it should be up on both sides. Or are there any questions on that part? Most of the time students have no issues on this. This is the part that's kind of the easy part. It's step 2 really is the problem, is where we try and set this thing equal to 0. All right, so when we go and look at this, here we go. Set it equal to 0. The first thing I'm going to do is what we do for factoring all the time, and that's GCF. So do you all see a common factor for all four of these terms? Something they have in common?
Yeah, 2.
2, they all have a 2. Okay, I agree. How about X's?
Just 1X.
They all have 1 X, right? Just 1. So I can pull a 2 and an X out. And now what I need is to have enough space for 4 terms here so that when I multiply this 2x through to these four things I put here, I should get back this. So what do you have to multiply 2x by to get 2x to the fourth? So what's the only thing you're missing? You have the 2, you have 1x. You need how many more x's?
It's x to the third power.
X to the third power. So you need x cubed here. And then you say same thing. Excuse me, to try and make 2x become 12x cubed, you first have to turn the 2 into a 12. So you're going to have to multiply it times positive 6. And then you have to turn x into x cubed, so you're missing 2 x's, so I put x squared. On the next one, I have to turn 2x into negative 8x squared. So I'll need a negative 4. 2 times negative 4 will give me the negative 8. And let's see, I have 1x, I need 2 x's, so I'm going to have to put an x there. And then the last one, I have to turn 2 into negative 48. So I need a negative, what is that, 24 there? And I do not need anything else because I have an x and I need 1x, so I'm good. As long as I have that negative 24 there, we should be all right. All right, that good? So here's where things change, all right? We need to know how to factor this. And what you do is you count how many terms you have. We have 1, 2, 3, we have 4 terms, right? Anytime you have 4 terms and you're trying to factor, you use a technique called grouping. Okay, so I'm just going to put it over here just as a separate problem. What we're going to try and do is do this factoring technique called grouping on these 4 terms. Okay, so here's how grouping works. You look at the first 2 terms. Right after the second term, you kind of do like you're gonna break the problem up into 2 pieces, where you have the first 2 terms. You're kind of gonna isolate these, just kind of focus all your attention on those, and then you'll look at these separately. So in the first 2 terms, just in the first 2 terms, do you all see that these both have an x squared? So I'm just going to do a GCF. I'm going to pull a GCF out of just those 2. So if I pull x squared out of those, I'm left with here, well, same thing. I have to figure out what I multiply x squared by to become x cubed. I need an x. And then I say, what do I have to multiply x squared by to get plus 6x squared? So I need a plus 6. And then you do the same thing on the second terms. You see, what do these both have in common? Do you all see what these both have in common?
Negative 4.
Negative 4. So I can pull a negative 4 out. So I put minus 4. Then in parentheses, I'll have x plus 6 again. Because if I pull a negative 4 out here, if I multiply this through here and here, I'll get back this. Are there any questions on that step? The next step is the weird step. Once you've done this, and very important, if these 2 things match, which they do, okay, those 2 match, your next line will be this. You will write down what matches, and then in a separate parenthesis, you will put the 2 things that were in front in here, x squared minus 4. That step always looks weird to students, like how in the world does all of this become this? So we have 2 options in terms of understanding that. One, you can just believe it and just remember to do it, right? Just say, oh, if I see the same thing here, I write it down, and then I just write these 2 things in the parentheses and I'm done. And there's no thought to that. But if you actually want to know why it turns into this, I can explain it to you. But I need you to kind of think about a different problem for a moment. If I wrote down x squared times, let's say, y minus 4y, these both have the same thing in common, right? I mean, these both have a y in common, right? So I can pull a y out of both of these. And if I pull a y out in front, it'll turn into this. Do y'all understand what I'm doing here? So basically what I did here is exactly what we're doing here, except everything in yellow is like the y. See, you have x squared, right, times something, right? X squared times something, and then minus 4 times something. And since these are the same, I'm going to factor it out. I'm going to pull it out in front, just like we pulled that y out right here. So that's the x plus 6 out in front. And then the x squared minus 4 is what you'd get if you pulled that y out of both. That's what would be left. So if I pull the x plus 6 out of both of these, the x squared minus 4 is what's left. I hope that that makes sense. Again, if it doesn't, just you have to remember to do it. So there's one more step, unfortunately, because the x squared minus 4 happens to be a difference of squares. So I can break that down using that formula that we just talked about in the previous problem. This is something squared minus something squared. So we use difference of squares formula. And this is it. We're done. Well, we're done with this part. We have factored this. So now I come back over here and I say, all right, this is 2x. And then everything there turned into x plus 6 times x plus 2 times x minus 2 equals 0. And then I can set each of those equal to 0. So if I set that equal to 0, I get one answer, 0. If I set this equal to 0, I'll get negative 6. If I set that to 0, I get negative 2. And if I set that to 0, I get 2. So I have 4 x-intercepts. And now I just have to figure out whether or not I cross or bounce at these. So I go back and I look at the powers again on these, and all of them are 1s again. And since they're odd, I'll cross at all of them. At every single one. It doesn't always work out this way. You don't always like cross at all of them or bounce at all of them. Sometimes one of them bounces, the other one crosses. It just depends. Happens to be in this problem that we cross at all of them. Are there any questions? Y'all are awfully quiet today. I'm going to graph 0, 2, negative 2, and negative 6. There are my x-intercepts. Remember, the graph went up on both sides, right? Up on both sides. So that means over here it goes up, over here it goes up. And now I'm just going to connect all these dots together, but I'm going to cross through the x-axis every time I get to an x-intercept. So I'm going to cross through, cross through, cross through, cross through, and connect. And I told you last time that everyone's picture is going to look a little different, right? Someone else might draw it and it might look like this. They might come down further. They might go up higher. Here, they may decide not to go as high. They may flatten this out more. Everyone's graph will look slightly different. However, we will all have the same x-intercepts. Our end behavior will be the same, like what's happening on the ends. And then these little humps that we have should be the same in the sense that, but like all of our graphs should go like below the x-axis between negative 6 and negative 2. And all of our graphs should be above the x-axis between negative 2 and 0. And then below the x-axis over here, and then above back over here. That makes sense? Like there's going to be variations in our pictures. That's why it's a sketch. It's just a real quick, oh, I don't know if it's quick, but it's just a rough idea of what the function's doing. Okay. Y'all feel all right with us?
It's kind of crazy.
Yeah. So when it comes to these functions, right? When it comes to graphing these things, there are when the hardest step of these problems, and I think you would agree, the hardest step is this step right here, where you set it equal to 0, because then you have to factor. There are 3 different things there's actually 4 different things in factoring that I'm going to expect that you can do. You know, this step right here is going to require the factoring. So what I expect from you is that everyone here is comfortable with the GCF, right? That you can pull something out. I also expect that you can handle a difference of squares, right? That may come up. The next thing is the trinomial, which is like problems 33 and 34, which nobody asked me about. So I'm assuming y'all had no issues factoring the trinomials. And then the fourth thing is you could possibly have grouping, which is like what I just showed you on number 35. Did we do 35? I think we did 35. So just expect that when it comes to the sketching of the polynomials, that you're going to need to be somewhat comfortable with GCF, difference of squares, factoring trinomials, and grouping, because any of those things could show up on one of these problems. Okay.
I was going to ask about if we could do 33 real quick.
We can.
Okay.
We can, because I mean, we won't be able to do, the next thing we're going to do will be very difficult to do if we don't know how to do all of these types of problems. Okay. All right, so we want to make sure we're comfortable with them. Okay, so if we're going to do this, I'll move a little quickly. It goes down and up. In the middle, we don't know. Okay, so degree is odd, leading coefficient is 1. The hard part, set it equal to 0, right? This is step 2. So do we have a GCF?
I picked x squared.
X squared or x?
Yeah, x squared.
They would all need to have an x squared, right?
Oh, that's right. Yeah, we can't do that then. It would just be x.
Just x.
Okay.
And then when you do that, you'll be left with x squared plus x minus 12 equals 0. So you're just taking 1x away from each of these. So setting the first one equal to 0 is not a problem. This though, this x squared plus x minus 12, you have to factor, right? You have to somehow factor this. So this is a trinomial, tri meaning 3. There's 3 terms there, right? You'll see the 3 terms. Try. If you see 4 terms, you're going to try grouping. If you see 3 terms, you're going to do this method. So the method is you look at the number in front, right, which is a 1. You multiply it times this, which is negative 12. And then you look at the number in the middle, which is a positive 1. And what you need to do is come up with 2 numbers that multiply to be this and add up to be this. So this is just like a thinking exercise. You have to think, okay, what 2 numbers that I know multiply to be negative 12 but add up to be 1? So what are those?
4 and negative 3.
Positive 4 and negative 3 are your 2 numbers. If you multiply them, you get negative 12, right? If you add them up, you get 1. So once you've done that, once you've found those 2 numbers, all you have to do is put an x here and an x here in 2 parentheses, and then you just put these 2 numbers, plus 4, minus 3. And that's it. That's what's going to go here. We have x, then we have x plus 4, then we have x minus 3 equals 0, which we'll continue and we'll finish this off. But I just want to show you, like, if you don't believe this is right, just if you multiply this through, if you FOIL, you get x squared, you get minus 3x, you get plus 4x, and then you get minus 12. And if you put those 2 together, you get just an x in the middle and then minus 12. And you can see that that's what we started with. So I'm just trying to convince you that this does work, okay? That this does turn into this, but you have to use this little method here. So now I set these equal to 0. If I do that, I can get the answers. I'm not showing this step. I'm assuming you can just take those and set them equal to 0. And then I have to figure out bouncing and crossing, which again is kind of boring at this point. They all cross, okay? Because they all have powers of 1 on them. So I go graph. 0, 3, -4. Do y'all see how I don't really care like too much about how this looks? Like I'm not sitting here counting 1, 2, 3, and I'm just making sure they're in the right order because it's just a rough sketch, all right? I know my left side goes down and my right side goes up, and I'm crossing through at each one. So I'm gonna cross through, I'm gonna go crazy here. I'm gonna come back down, and then I'm gonna go like this. There, I just felt like doing that. All right, we good? So now I've officially done like pretty much every variety of problems that I would test you on, okay? I'll show you something. Do you remember how I told you how this class is different than there's 2 algebra classes, right? I told you all that. So in my algebra class yesterday, we did this same topic. You want to see the function they're graphing? I'll show you it. Here's their function. X to the 6th minus 9x to the 5th plus 17x to the 4th plus 33x cubed minus 90x squared. So they have to solve this equation. Like they have to set this equal to 0 and solve it, which is a much more difficult thing to do because we're sticking in this class to really 3 things. Difference of, GCF, okay. Difference of squares, trinomial, and 4 terms, but we're stopping there. No more than 4 terms. Look at what they have to do. There's 1, 2, 3, 4, there's 5 terms here, right? So they've got to factor that. So there's a whole other method for doing it. This is the method. This was their homework problem. That's their other homework problem. Oh no, so those are their 3 homework problems to try and graph. So what I'm getting at, what I'm trying to say is that we're keeping this very narrow or focus on problems that only require certain skills, right? The different squares, the trinomial, and the grouping. That's it. We'll keep it there. And I promise you, I won't go outside of that. All right?
The funny thing is, I still have my notes on how to do it, how to do the other ones.
Yeah, and it requires a whole new method of factoring. And
I remember doing those. They were a nightmare to do. They took so long.
They take forever. Yep. Which is why I only gave them a few problems. Okay, here we go. So we're ready to move on to the next type of function that we want to graph. And I'm just going to remind you, because I think it's always good to kind of take a step back and think about what we're trying to accomplish here. What we've done so far in this class is we've learned that we can graph a line, right? We know how to graph a line. So what can we sketch, right? What can we sketch at this point if we were asked to? What types of functions can we do? Well, we can do a line, right? So if I gave you something like f of x equals 5x minus 4, I would trust everyone could draw that, probably using the fact that the y-intercept is -4, the slope is 5, and then you could do a point and rise over run, right? I know it was a while ago, but I expect that you could do that. Quadratic functions. Something like that would be something I would expect you could do. And to do that, there's a whole set of steps, right? I gave you a whole set of steps for that. Does it open up or down? What's the vertex? Do a quick sketch. Go find your x-intercepts. Go find your y-intercepts. Draw your picture. Okay, so we have a whole set of steps that are completely different, right? What you do to graph a line is completely different than what you do to graph a quadratic function. And now what we've looked at is polynomials, right? Which is f of x equals, and then here I'm just going to put question mark because polynomial can look like a lot of things. But our method is, use that table to figure out what the left and right looks like. Find your x-intercepts, find your multiplicity, bounce cross, and then draw your picture, right? And now what we're moving on to is our next type of function, which are called rational functions. And just so you know where we're headed, okay, this is today, all right? Where we're headed is we're going to do two more, exponential and logarithmic. And so the idea is that when you finish a college algebra class and you move into pre-calculus, you know, if you were moving into pre-calculus, which no one is, the idea is that you have a pretty good idea of this kind of like, these are kind of our classic functions. These are the things we run into a lot. And so you kind of have an idea of how to draw them and what they look like and, you know, what the pros and cons are for each one. I think I've spent enough time talking about like where in the real world you would see lines, you know, cost functions for electricity, quadratics, parabolas, right? Throw an object through the air. Polynomials are more like, you know, cost functions or profit functions for a business or the stock market, things that are fluctuating up and down. Rational functions are the new ones today. So the natural question is, you know, what do they look like? Where are they useful, right? Where do we see them, right? So I'm going to start this with a thought exercise here. When I say probability, I want to make sure you understand what I mean. So like if I take a coin out of my pocket, if I take a quarter out and I tell you I'm going to flip it, okay? When we say probability, if I were to say, what's the probability that I'm going to get a heads? What would you say?
50-50.
50-50. So 50% chance, right? 50% chance that I'm going to get a heads, 50% chance I'm going to get a tails, right? So 50-50. When we think about 50-50, really the idea of 50%, right? So if I have a coin flip, right? If I do a coin flip, you're going to say it's 50% chance of heads and 50% chance of tails. 50% really means 0.50, right? If we converted the percent to a decimal, which is really 1/2. Okay, 1/2 is 0.5. And so is this one, it's 1/2. So in other words, if you flipped a coin, there's a 1 out of 2 chance, right? 1 out of 2, there's two possible outcomes, and one of them could be heads. Here, there's 2 possible outcomes, and one of them could be tails. So saying 50% is the same as saying 1 out of 2. Agreed? For 0.5? So if I were to kind of give you a visual of what's happening here, if this is heads, and this is tails, and this is the probability here, would it make sense to you to say that the chance of a heads is 1/2? Oops. So I could draw like a little bar that says the chance of this heads is 1/2, and the chance of the tails is 1/2. Does that visual make sense to you? The height, how tall that is actually your probability?
Yes.
Yes. Okay. Everyone got that? Same height here, so same probability. All right. Okay, so with that basic idea of probability, I'm gonna ask you to consider this. Think about human beings, all right? Just think about a human being on planet Earth right now, okay? I'm going to draw you a graph. I want this x-axis to represent time in years. And then this axis is going to represent the probability that this person is alive. Okay, so think about it this way. Let's say that somebody is born, okay? And they're born alive. So we're not going to get into a debate here today about when life begins and all that shit. We're not even going there, okay? Let's just say that we all agree that there is a time where we can say this thing is alive, right? Look, this person, right, is existing. Here it is at time 0. So we start the clock. So what is the probability in general? Okay, just in general, what is the probability going to do as we move to the right on this? So as time goes on, what is the probability that somebody is alive? What does it do?
Decreases.
It what?
It decreases.
It decreases. Okay, so I mean, and we could start to get real anal about this, like, because babies are kind of at jeopardy of dying. Like getting through the first couple of weeks is kind of a danger zone for kids. So there is a lower probability. If you can get past the first few weeks, then you know you might have better chance of living, right? So we can say that maybe there's some fluctuations here. Okay, whatever. We could argue that. But let's talk about, 10 years down the road. There's a pretty good chance that a person will live to be 10, right? Just in general. In general. So what about the probability that someone will live to be 50? How would that compare to being, living to be 10? Higher or lower?
It would be lower.
Lower, right? Not everybody lives to be 50, right? Most people live to be 10, but not everyone lives to be 50. Some people die, right? So the probability is going to drop, right? Okay. What about 75? What's the probability? Lower or higher than 50?
Pretty low.
Pretty low? Okay. Y'all with me? Y'all understand what this graph represents? I'm not talking about one person in particular. I'm just talking about in general, like human beings. Let's go to 100. What's the probability that a human lives to be 100? Lower than 75, right? Would you agree? Definitely lower than 75. It's probably going to start dropping off pretty quick here. And we're not talking, I haven't even talked about like whether or not we're talking about people in different regions of the world, because lifespans vary. Lifespans vary in different parts of the world, depending on where you are. If you're growing up in the United States, you're going to have a longer expected lifespan than somebody who's growing up in like some third world country where, clean water's not even available, right? So we're just on average, okay? On average. What about 110?
That's very slim. Not very many people
slim.
make it. Yeah, people don't even really make it past 90.
Yeah, but there's a probability though, right? I mean, there's a chance.
Yeah,
that
it's slim chance.
Slim chance. You got a slim chance. I don't think I want to see 110 personally. I don't even think I want to see 100. Maybe 80. I'd be okay at 80. That'd be fine with me. All right, so 110, but do we all agree, this is important, do we all agree that there is some chance? Does anyone disagree? Does anyone think that there is no chance? Okay. 125. What do you think?
No chance.
No chance?
There could be a very, very slight chance.
Very,
I think
very
like 1 in a million or something.
Isn't that like the world record for the oldest person or something like that?
I'm not sure what the world record is, but we're starting to get closer past that world record. So I have the same question for you. Does anybody here think that the probability is 0? Like no chance, no chance. So everyone agrees that there is some chance?
It's possible.
It is possible, very slim chance. I heard someone say 1 in a million. It's probably lower than that, but the idea, 1 in a million, right? Okay, so we still have some probability here, right?
Longest is 122 and 164 days.
I'm sorry, the world record, what is it? 122? Is that what you said?
Yeah, it's 122 and like 100 and something days.
Yeah, okay. All right, let's keep going.
The oldest verified person to have ever lived was 122 years old. and 164 days. However, there are people that have claimed that or had family that lived longer.
Okay.
But that's the oldest verified person.
Yeah. Well, what do you think about 200 then?
Very, very, very slim. If
We
it's,
should not live that long.
I think
Okay, so
they'd be like,
let me
I
ask the
think it would
question
be-
again. Let me ask the question again. Who thinks there's no chance that someone can live to be 200? No chance at all.
I think there's no chance.
I do.
You think there's no chance?
Nowadays, no.
Okay, so let me ask you this. If you don't think there's any chance, how about 199?
No.
I think
198?
after like 130, it's a zero chance.
You think 130 is where you would be zero?
Okay, maybe like 135, but even then,
135. You see how that gets hard to figure out where it would actually be zero, right? So here's the thing. Let me ask you this. For those of you who think there's no chance to live to be 100, okay? I mean, sorry, 200. There's people here that are saying no way, right? No way. 0% chance of this. I want you to consider something completely different now. If I go play the lottery tonight, is there a chance I can win?
Yes.
Not
yeah, but it's actually it's like super. You know, you have a higher chance of getting into a car accident.
Yeah,
But
getting struck by.
could I win?
You could possibly,
Okay.
It'd be like 0.00001%.
But there's a chance, right?
Yes.
Okay, so what do you think about this? What do you think the probability is that tonight I go win the lottery, and then as I'm walking out to walking out to take my trash out tonight, I get struck by lightning and live? Could it happen?
Yes, theoretically it could happen.
It could happen, couldn't it? Now, what are the chances? Infinitesimally small, right? But you can't say zero because it could happen, right? I could win the lottery tonight. I could get struck by lightning and live. It could happen. And because it could happen, you have to assign some infinitesimally small probability to it. You can't say zero because zero means no way. Can't happen. And you can't say it can't happen. So you want to talk about infinitesimally small. What do you think the chances of me winning the lottery tonight and then playing it again the next day and winning again? And doing that for 30 days in a row and winning every day. Could it happen?
Theoretically, yes.
Theoretically, right? There has to be a probability. You can't say zero. So we start to get to this. What I'm trying to get you to see is that even though nobody has ever lived to 200, and even though it seems insane to think that there's any chance, there is. But we're talking about like an infinitesimally small chance. So small that you might have a better probability of winning the lottery, being struck by lightning and living. Like that might be a greater chance than you living to be 200. Do y'all understand what I'm saying? Like it's a weird concept, but it's an important concept in the real world because this is the way probabilities work. So what's happening here, at the end of the day, what you need to understand here is this graph is getting smaller and smaller and smaller and smaller and smaller and getting closer and closer and closer to zero and never getting there. All right, do you understand that idea? I'm going to draw you a picture with a computer.
Is it kind of like dividing by 2? So technically it'd never be 0.
Like you just keep on halving it each time. You could think of it that way. You could think of it that way. Here's a graph that's doing this, okay? Look at this graph. As you move to the right, it starts diving down, right? It goes down and down and down. And as you keep going to the right, it keeps getting smaller and smaller, right? If I ask for the value, look at that. This is saying if I plug in 23, I get an answer of 0.043. Okay, so this point right here, is 23. And then the y coordinate is 0.043. If I go a little bit to the right of it over here, that's 24 and then 0.042, it got smaller. Understand? But if I keep going out, let's keep going out here. Way, way out here. And let me zoom in so you can see it here. It has not actually reached 0 yet. There we go. Now you can see this. So if I go here to this point, look at how small it is. 0.00071, right? That's a very, very small number, but it's not 0. And I can just keep doing this on this graph. I can go out as far as you want me to go. You want me to go out to 1 million, I can go out to 1 million, doesn't matter. If I go out here, I look at that. Now look at the computer. Look at what the computer's saying. What are they saying the Y value is there? It's saying 0, and that's because it's 0.000 with so many zeros and then some numbers that the computer says, well, that's close enough to 0. But in reality, it's not. There is a gap in here. I wonder if we can zoom in far enough to see the gap. Do y'all have a cell phone? Yes, of course you do, right? You know when you get your cell phone and the battery like holds a charge and it's like awesome, your battery will last for like 3 days when you first get your phone, and after a while, right, your battery starts to suck, right? And then you have to go get a new phone because your battery is crap now. You know what I'm saying? Or am I the only one who's ever had that happen to them?
I've had
No,
that
that's how my
happen.
phone is right now.
So if you go time here and you go, you know, I don't know how to say this, the probability, let's just say the time your phone holds a charge, right? Holds charge. So we know that in the beginning, you get your phone, it's like awesome. And then over time, it starts to drop down, right? But if you look at it as a probability, right? There is a chance that right? That your phone lasts for the next 20 years. You turn it on, it comes on, right? Now, it may not hold the charge very well, but it may last. Think about the light bulbs in your room, right? Every once in a while, you have to replace the light bulb, right? So how long is the light bulb going to last? Well, what's the chance it's going to last the first week you buy it? Pretty good, right? It's going to last 4 months? Not as good as in the first week, but as time goes on, that probability drops. All right, I think I've beat this to death. Y'all understand this idea?
Yes.
Okay. So in the real world, we have these things that do this, right? And do we have a function right now? Have we learned a function that behaves this way? So do lines do this thing where it drops down and kind of flattens out? No, they're just lines, right? Parabolas, they go up or down, right? They don't do this either. Polynomials, they wiggle around up and down, but the ends go up or down, right? Right now, we have no function in our arsenal that would actually deal with a real world situation like this. This is not a line. This is not a parabola. This is not a polynomial. So we need a function that behaves this way. And that's where rational functions come in. They help us model things in the real world that behave like this. Here's another thing for you to consider. Let me try and think of how I want to formulate this idea. I'm trying to give you a problem that you can understand, but at the same time, it's not too complicated. Let's talk about air pollution. Okay, let's talk about air pollution. So we know that the air around us is made up of a lot of things, right? A lot of good things we need and a lot of bad things, right? So there's a way that we could if you were to take a balloon that's full of air from outside and take it to a laboratory. There is a way to take that air and purify it and take out all the bad stuff and just have whatever you want, whether it be just the oxygen or just the, you know, carbon dioxide, whatever you want, you can isolate things, right? Does that make sense? You could clean the air if you had just a balloon full of air. Yes? So what I'd like to do is think about this. Think about all the air on the planet, all right? And our x-axis is going to be the percent we want to clean. And this axis is the cost, how much it'll cost us to do that. So if we want to clean 0% of the air, right? So the air's out here right now, it's all around us. If we wanted to clean it, take out all the bad stuff. If we wanted to clean 0% of it, it wouldn't cost us anything, would it? We just let it be. There's no cost if we're not going to clean anything. How much would it cost to clean 1% of all of the air around us? Well, it would be expensive, wouldn't it? To clean just 1%, but it would not be zero. So it'd be like, you know, whatever the cost is. Maybe this is like $1 billion. How much would it cost to clean 10% of the air? More expensive than 1%, right? Okay, so now it's going to be higher. What about to clean 50% of the air? Even higher, right? Now, here's the tricky part. Could you ever clean 100% of the air? Could you?
No.
I don't think you could, right? Because it would be constantly becoming dirty with other things, right? So like you could never actually clean it all. So the cost would continue to go up and up and up and up and up. But there's like this imaginary line that we can never get to. And so this graph, what it does is it just gets more and more expensive. And we can never truly achieve 100%. And the graph just goes up and up and up forever.
Like being 100% clean from germs.
Pardon me?
Like being 100% clean from germs.
Exactly. You just could never do it all. Maybe you could clean half the air. Maybe you could clean 10%, but there's no way you could reach 100%. It would just become feasibly, money-wise, it'd become impossible to do. The cost would become infinite. So this is a function, if you look at this red function, this is a function that what it does is there's this like, look at this dotted line is like this wall, like a barrier. And your function cannot see, the function doesn't seem to want to cross it. It just keeps going up and up and up. Do we have a function that we've learned that does this? Well, lines do this, right? So a line would eventually go through that, wouldn't it? And a parabola does this. And eventually, even though it goes up and up and up, it keeps moving to the right at the same time. So it doesn't, even though it kind of looks like this red one just keeps going up and up and up, but it can never get past this line. The parabola does. So that doesn't work. Polynomial doesn't work either. Okay? So rational functions are perfect for the two situations that I've just given you, where you have something that kind of dies down or something that goes up forever. So going back to this graph, let me go back to this. Can't even see it anymore. Let me just zoom in on this. There we go. So look at this graph. Look at its basic behavior. As we go out to the right, the graph dives down and gets closer and closer to the x-axis. As we go out to the left, the graph is getting closer and closer to the x-axis, but from the bottom. You see that? It's actually below the x-axis, moving closer and closer up to the x-axis. And then as we move towards the middle, towards the center here, the graph dives down. And then as we move to the center from the right side, the graph is taking off and going up. And so we almost have like this imaginary wall in the middle where the graph is like, doesn't want to hit the wall. So it just kind of like turns and takes off. Y'all see that visually? What I'm trying to describe here? This vertical thing is like a vertical barrier. Right? It's this vertical barrier that our graph, when it comes to it, is like shit and like has to do something and just like takes off, goes down or up. And then as we go out to the left and to the right on both sides, it's almost like there's an imaginary line here. This imaginary line is almost like a magnet. I like to think of it as a magnet. You know how magnets, pull things together? This magnet's like your graph is out here and it's getting pulled closer and closer to this magnetic line. And it gets closer and closer, but it never is allowed to touch. And it's happening at both ends. This is the general idea of a rational function. You've got these vertical barriers. You've got these magnetic lines that pull your graph towards it. Those are the main two things on a rational function. So now that I've kind of confused you, let's actually look at what a rational function must look like. All right, so what is a rational function when you write it down? So here we go. So a rational function is this. It's a function. All it is, it's pretty simple. It's just a fraction where the top is a polynomial and the bottom is a polynomial. And that's it. That's what a rational function is. So there's good news and bad news here. The good news is that it's a very simple idea. The bad news is that this can be bad. Like this can be really ugly. Because polynomials are what we just studied, right? We just looked at polynomials. I had you graph polynomials for homework. We've done three or four problems today. This is saying if we take two different polynomials and put them into a fraction, you are now creating a rational function. So I'm going to give you now specific examples. As an example, here is one type of rational function. Let's do this one. Let's make that x squared minus 9 on the bottom, just to make our lives a little bit better. So this is an example of a rational function because we have a polynomial on top and a polynomial on the bottom. You'll see that? Two polynomials create a fraction. That is one example. Another example would be, I don't know, why don't we take that same thing, but this time flip it over. Let's do x squared minus 9 on the top and x squared plus 1 on the bottom. Do you think that these graphs look anything the same? Do you think they're similar to one another? Or all I did was flip them over. Do you think the graphs look similar?
I think so.
Yeah, maybe. Let's look at them. I'm going to graph these for you because I want you to see just how freaking ugly these things are. All right. Okay, the first one is x plus 1 over, oops, that's not going to work. X plus 1 over x squared minus 9. Okay, there's the graph of the first one. We're going to have to try and graph this, all right? It's not going to be fun. Here's the other one. Rational functions are the hardest functions to graph. Out of all the functions we'll do in this class, they're the hardest. The blue one is the other one. All I did was flipped it over. Do they look anything the same? Not at all. Not at all. I mean, you're right to think, yeah, I mean, how different can they be? All you're doing is flipping them, but there is a huge difference between the two. You see that? So our goal, okay, and this isn't going to happen today, okay, so we don't have enough time to do this today, but our goal is going to be able to graph rational functions by hand. And it's going to be tedious, but like the polynomials, I'm going to keep them kind of at a certain level so they don't get too messy. But there's a lot of things you need to understand about them before we can do them. Let me give you another example. Let's do this. How about, as an example here, just so you can kind of see, what about this one? How about x squared minus 25 over x squared minus 2x. I'll make it x squared minus 7x, sorry. Is that a polynomial over a polynomial? Yeah, so this is a rational function, all right? We'll look at this one now, just as our last one. Then I'm going to start to, what I'm going to do for the rest of the day is I'm going to just get you to, I'm going to write the steps down. We're going to talk about the steps. I don't think we'll actually get to graph one today. But let's just write that. Let's see what this one looks like. So this one is x squared minus 25 over x squared minus 7x. Okay, let me hide the other ones. So that green one is this one. So we have some work ahead of us here, right? If we're going to have any hope of graphing these sorts of things, we've got a lot of things to kind of learn, right? Okay, so let's start setting up the ideas here. So what I'd like to do is I'd like for us to look at these three functions. This is going to be a lot of just thinking right now. I'd like for you to look at these. Let's look at this very first one, okay? Let's look at this very first one, and let's go back to the graph. That's this graph right here. Okay, let me zoom in a little bit more. There we go. Okay, so I'd like for you to think about something. We're looking at this one right here. Let me write it down so you can have it. F of x equals x plus 1 over x squared minus 9. Okay, look at the numerator of this, okay? X plus 1. If I asked you to set that equal to 0, what would be your answer? If I asked you what x makes this 0, what would you tell me?
-1.
-1, right? So I want you to go to -1 on the x-axis right now and tell me what you see. What do you see there at x equals -1? What is it?
That's where it switches from the one that's going down to the one that looks like kind of like an S. Like the one
Okay,
with the
but
curve,
what is this
the
point
curves.
right here? What is this
Oh
point?
wait, that's 0. Never
That's
mind.
an X-intercept, right?
I was looking at the wrong one.
Oh, okay. So what I'm asking everyone, just to be
It's
clear,
0.
I was asking what makes this 0, right? So if you set that equal to 0, you get -1, right? And if I go to -1 on the x-axis, here's -1. Do y'all see we have an x-intercept there? Do you think that's a coincidence that what makes the numerator 0 is also where we have an x-intercept? Think that's a coincidence? I don't know, maybe it is. Let's look at the next problem. Let's look at this other graph. This is the function f of x equals x squared minus 9 over x plus 1. Think about what would make this numerator 0. What would make that top 0 there?
3 or -3.
3 or -3, right? So you could factor this as a difference of squares and set each one of them equal to 0, and you get 2 answers, 3 and -3. Do y'all see where those are on this graph? Those are x-intercepts again. It seems like wherever the numerator is 0 corresponds to where we have x-intercepts. Let's check one more. Looking at this last one, x squared minus 25 over x squared minus 7. On this one right here, where would we have x-intercepts if this follows what these two have done? Where should we expect to see x-intercepts? What numbers make x squared minus 25 0?
5.
5 and?
Oh, -5.
-5, right? Good. So let's look at the graph. Here's the graph. Hey, look at that. Here's -5, right? And here's 5. So we've got something interesting happening here. Wherever the numerator is 0, we should have an x-intercept. Do you all follow me? Wherever the numerator is 0, we should have an x-intercept. I'm going to write all this down in a minute. I'm just trying to get you to see it visually. Wherever the numerator is 0, it looks like we have an x-intercept. Okay, that's good. What about the denominator being 0? Let's go back to the first one here. What about the denominator this time? If I say, hey, what would make this denominator 0? What would you tell me?
3 and -3.
3 and -3, right? And do you see what's happening on this graph at 3 and -3? Something interesting. At x equals 3 and x equals -3, do you all see those things I was referring to a moment ago? Do you all see those vertical barriers? Do you all see that the graph, here's x equals 3, to the right of that, it goes up, to the left, it goes down. So it's like this vertical barrier, the graph was getting drawn, and then the graph was like, oh shit, I can't hit it. I've got to go somewhere. So it dips down on one side, and the other side, it goes up. Now, why it goes down and up, we'll talk about, but do you all see that where the denominator is 0 appears to be where we have these vertical barriers? What about on the next problem right here? On this one right here, where should we expect to see a vertical barrier? What would make the denominator 0?
-1.
-1, right? Okay, so let me show you the picture. Here's the picture. Well, let me draw I'm going to draw the line. Wait, I'm done. Let me draw this first. -1. Let me get this one out of here. Let me get that one out of here. So I'm about to draw this one, and we should expect to see a vertical barrier at -1. Is that what's happening? Let me zoom out. That is, right? So the graph is like, oh, I can't cross this vertical barrier. I got to go up. And on this side, it's like, oh, I can't go across that. It goes down. How about on this last one? If we take the denominator and ask ourselves, when is that 0? I could factor out an x GCF, and I would have what 2 solutions here?
0 and 7.
0 and 7, right? 0 and 7. So if I graph this right now, I should expect to see vertical barriers at 0 and 7. Let me see if that's right. 0, 7. Here are my vertical barriers. Let me take that graph out of here. Zoom in a little bit here. It's hard to see the one at 0. Right? It's kind of hard to see that. But here's a graph. Look at that. That's exactly where they are, right? It's exactly where they are. So to recap, when you have a rational function, wherever the numerator is 0, you should expect x-intercepts. Wherever the denominator is 0, you should expect vertical barriers. Let's go ahead and write that down. So sketching rational functions. So the first step to sketch a rational function is to find the x-intercepts. And how am I going to do that? Maybe you tell me. How will I find the x-intercepts on a rational function?
You look at the, oh, sorry, go ahead.
Oh, you go.
You look at the numerator. And then
set it to 0, right?
Yeah.
Just set the numerator to 0. Set the numerator, which is the top, equal to 0 and solve. And just remember, these are the answers are points on the x-axis. Okay, just remember that. Whatever answers you get, you're going to take the numerator, set it equal to 0. Whatever answers you get, that's where your x-intercepts are. Okay, step 2. You're going to find the vertical barriers. Now, in math, we don't use vertical barriers as the name of these things. We actually have a name for these. They're called vertical barriers. I'm going to keep that there. I don't want you to necessarily not think that way, but we call them, the mathematical term for those is vertical. Let me write it first. It's called a vertical asymptote. It's a weird word. Asymptote. Asymptote. It's like the M and P are kind of like silent in some way. Asymptote. Asymptote. Say it real fast, no one will care. Asymptote. So we're going to find those vertical barriers, which are actually called vertical asymptotes. I'm going to refer to these from here on out as VAs. Okay, so we don't have to write it down. So how do we find those vertical barriers? What did we say we were going to do? Not the numerator, right? Now we're going to look at the denominator. So we're going to set the denominator equal to 0. And solve. Very important though, whatever answers you get here, the answers are not going to be points on our graph. These are vertical dotted lines. Right? Our graph turns up or down here. I haven't explained how you can determine that, but it's just important to know that the vertical barriers are not actually part of your graph, right? These vertical lines are not part of the graph. The graph is the green part. These are just kind of imaginary. They're there, but they're not there. We are going to use them to help us graph, but they're technically not part of the graph. Understand? Okay, so we're almost out of time. That's it. So here's what I want you to do for homework. I'm going to give you some functions right now. And all I want you to do are the first 2 steps. I want you to take these and find both the vertical and horizontal, both the x-intercepts and vertical asymptotes for these functions. This is the only homework I want you to do tonight. So homework. Find the x-intercepts and the vertical asymptotes for, okay, problem 1. F of x equals 2x minus 4 over x squared minus 6x. Number 2, f of x equals x squared minus 6x minus 7. Hold on, I'm thinking. Over x squared minus 2x minus 8. Third one, f of x equals x cubed. No, you know what? We'll do it this way. Let's do x squared minus 4x minus 5. Sorry, I forgot to put minus 5 up there. Over x cubed minus 9x. I'm going to give you one more. Okay, there we go. So basically this homework assignment isn't very complicated in the sense of all I really am asking you to do is solve a bunch of equations, right? That's all I'm asking you to do. I want you to find the x-intercepts. How do you do that? You're just going to take the numerators, each of these numerators, and set them equal to 0. So you've got to solve 4 equations to find the x-intercepts. And then to find the vertical asymptotes, you're going to look at the denominators and set them equal to 0. So you've got to be able to solve those equations. So there's a total of 8 equations you have to solve. All of them are going to require some sort of technique, you know, factoring. So see how that goes. Make sure you do this homework, because next class, what I'm going to do is in the beginning, I'm just going to call on people and just be like, hey, okay, so let's, because we're going to want to graph these. So I'm going to ask you for your answers. Any questions on what you're going to do? We have a lot to do with this still. All right, everyone. Have a great day.
Bye.
Thank you.
Thank you.
Thank you.
Good one.